Hello, welcome. In this video we are going to state and prove two results on a topological property. First of all we are going to show that first countability, it's a property of a topological spaces. First countability is a topological property. We will also, after that, we will show that second countability is also a topological property. So to prove that first countability is a topological property, we have to choose two spaces x and y, two topological spaces x and y, and the first space is supposed to be a first countable space. So x be a first countable space we choose, and the second space y, it is chosen such that it is a homeomorphic image of x, and that means y is homeomorphic to x, or x and y are topologically equivalent. Then clearly there exists a function f. It's a homeomorphism. There exists a function, a homeomorphism f from x to y. We shall now prove that y is first countable. Now it's enough to show that y is first countable using the fact that x is first countable. So in the proof we can use the facts, available facts. First one is first thing that we know about x is it is first countable, and we also know that x and y are homeomorphic, are topologically equivalent. But there exists a homeomorphism from x to y, homeomorphism from x to y. F is that homeomorphism. But how can we show that y is first countable? If you want to show that a space is first countable, you have to choose a member, an element of that space. Here we are choosing an element a of y, and then after choosing that, if you can, this element is arbitrarily chosen. See, it's because whatever we prove about that element chosen, it must be automatically it must be true for every other element, every other member of that space. So and that means we want to prove we want to prove the statement that the following statements that we want to here we are going to prove all the statements must be true for every point belonging to that space. Here the space is y, the second space. So for that we arbitrarily choose an element a, and about that that arbitrarily chosen element we will develop that steps of the proof. We will prove all the things, and after completing that, then since the element is chosen arbitrarily, see every steps that is stated and proved about that point will automatically be true for all the remaining elements. Okay, so let a be arbitrarily chosen, be an element arbitrarily chosen element of y. Then what we actually want, we want a local basis. See, we want a local basis for the element a. That is the thing actually we are trying to do. We want a local basis for, or we want to show that there is a local basis for the element a. After completing that, after completing the existence and the proof for the existence of the local basis for the at the point a in y, then it will automatically get that there exists local basis for each and every point belonging to the space y. So let's choose a arbitrarily, an element a of y is chosen. Then we know that in the inverse, by applying f inverse, inverse image of the element a, that will be in x. So clearly f inverse of a is in x. It's that means it's a point in x. So f inverse a is a point in x. But we know that x is first countable. So this property is there. since x is first countable, and also f inverse a is a point in x, and we know we can say that there x is a local basis for the point f inverse a in x. So there x is a local basis, and which is countable. That must be countable also. So there must be there x is a countable local basis for the point for the point f inverse a in x. And that countable local basis is taken here as script b. It's a collection of countable local basis, means the local it contains open sets which contains a collection of open sets, a countable collection of open sets which contains the point f inverse a. So we write that it has that collection is represented by, we write it, or we represent that collection by script b. Then it is then indexed using f inverse of a. It is then named using f inverse of a. So the collection is denoted by script b f inverse a at the point f inverse of a. Using this fact, using the existence of this countable local basis, we shall prove that there exists a countable local basis for the element a which is chosen in y. And that local basis can be given as script ba, and script ba contains the images of the members of the first this local basis, script b a inverse f inverse of a. See, this local basis contains members, open sets, and these the open sets which are members of this local basis are denoted by b. Arbitrarily it is denoted by a typical element is denoted by b. So b is an element of script b f inverse of a. Then we consider the images of the open set using the function, applying the function f, applying the homeomorphism f. So f of b, we get f of b. Thus we define script b a equal to set f of b, where b is an element of, b is a typical element of the local basis script b f inverse of a. And thus we get it's a collection of open sets. It's a collection of open sets in y. It's because f is the function f is an open mapping, and b is an open set. We know that b is an open set, and since f is an open mapping, so f of b is an open set. Thus this is a collection of it's a collection of open sets, open subsets of the second space y. It's countable also. Why? Because the members of the members of this set is countable. Because it's a countable local basis, so the members are countable, and therefore this set is the new set is obtained as the image of by choosing the image of the members of this set. Therefore the second set is also countable. It contains countable number of open sets. Since f inverse of a is an element of b for each b in script b f inverse of a, we also know that f inverse of a, where is actually f inverse a? F inverse a is in the space x. So f inverse of a, which is a member of the space x, and we know that script b f inverse of a is a local basis for the element f inverse of a. It is very clear that f inverse of a, that point f inverse of a, is a member of every element of this every member of this local basis, every element of this local basis actually. And therefore therefore you can by applying f on both sides, see we can say we can write that a is an element of, we can easily obtain that a is an element of f of b. So using this, or this implies that a is an element of f of b for each fb. This is true for each fb belonging to script ba. Thus a is a member of fb. A is a member of fb where fb is an element of script ba. Now we choose an open set. Let us choose an open set. Let O be an open set containing A. So A must be a subset of Y because A is an element of Y. So we choose an open set O, which contains the point A. The f inverse of I. Then consider f inverse of O. Next consider f inverse of O. It's an open set containing f inverse of A. It's because O is an open subset of Y which contains A. Therefore f inverse of O is an open subset of X. F inverse of O is an open subset of X which contains f inverse of E. So there exists is a member of script B f inverse of A. There, because fa has a local basis. So since f inverse of A has a local basis, script B f inverse of A, and f inverse of O is an open set in X that contains the point f inverse of A. It is very clear that there exists some element in the local basis, the countable local basis script B f inverse of A, such that B is a subset of f inverse of that open set. B is a subset of that open set. See, B is a subset of the open set is f inverse of O. So there is a member. Therefore, there exists a member FB. See. You can now apply the effect of you can apply f on both sides here, and then we get that FB is a subset of thus we get that FB is a since B is an element of that countable basis, f of B will be a member of the second collection. Here we have two collections here. First collection is a countable basis for X, for X which contains f inverse of A. Okay, or with respect to the point, for the point f inverse of A, which is a member of X, and the second collection is script BA equal to FB, where B is an element of script B f inverse of A. Okay, now B is FB will be a member of. Thus we get that. Here applying f on both sides, we get FB. FB is an element of script BA. That is the second collection. This collection exists in the space Y. So this FB is an element of script BA, such that FB is a subset of O. It's very clear because if we can apply f here, f of B is a subset of when you apply f here, we get that effect of f is released here, is removed here, and we get that FB is a subset of O. This proves that script BA acts as a local basis for A. Since the choice of A is arbitrary, there is a countable local basis at each and every point of the space Y, and that means Y is first countable. Okay. Next, we proceed to prove that second countability is also a topological property. Here also we have to choose two spaces X and Y. First space X, that is second countable. In addition to that, it is second countable. Yeah. Additionally, it's a space. In addition to that, it's a space. X a space. It's a second countable space. So we choose X as a second countable topological space, and then we also choose the second space Y, which is topologically equivalent to X. That means there exists a homeomorphism defined from X to Y. Then we want to show that the space Y is also second countable using the facts, using all the available points about X and the relationship between Y, X and Y. We have to show that the space Y is a second countable. Since X is first countable, since X is a second countable, there exists a countable basis for the space X. Here it is given that X is a second countable, so there exists a countable basis for X, and that basis is taken here as script B. Let script B be a countable basis for X. Then that basis contains open sets. See, satisfying the conditions of a countable basis, satisfying the condition for a basis. There exists open sets, collection of open sets, and all those open sets are taken in script B. Next we define a related collection of open sets. Related collection of open sets means a collection of open sets that is related to the script B, the first collection, and that is defined as B prime. Script B prime equal to f of B. F of B because script B contains open sets. Typically, an element of script B can be taken equal to B. So B is an element of script B. Then you know that f of B is a subset of Y, because f is defined from X to Y. So f of B is a subset of Y. It's open also. Why? Because f is open. The function f is since f is a homeomorphism, the function f is open. Therefore, FB is open. The collection is so thus the collection FB collection containing FB, where B is an element of script B, is a collection of open sets. So B prime is a collection of open sets. Thus we have obtained a suitable candidate, a possible candidate for a countable collection of open sets, a countable collection of open sets that can act as a basis for the space Y. First of all, we shall show that script B prime, yes, script B prime is countable. It's so because script B contains only a countable number of open sets, so it is countable. Since script B is countable, clearly because it contains the images of members of B, it is clear that the number of elements of this set is also countable. Why? Because f is 1 to 1. Okay. Therefore, thus we shall now show that this this collection B prime is a countable basis for Y. Since B is a countable, since B is countable, then B prime is countable. Yes, up to this point we have explained. Okay. Now we want to show that B prime is a script B prime is a basis. Actually, it makes a basis for Y. There, for this purpose, we have to show two important points. We have to prove 2 important points. First point is explained here in part A. For that, we want to show that the union of members of script B prime equal to the space Y. That is, we want to show that Y is equal to union of the elements of the second collection of open sets. For that, we use the theorem. We can use a previous theorem 321. Okay, and that the steps of the steps for this purpose is given here. See, that is the proof in the proof of the first part. Here we take the union of b prime. B prime is a member of is a typical member of the second space. Here union of b prime, it's a member of this space, and then union where b prime is an element of script b prime. It's equal to you know that the member all the members of b prime script b prime are of the form fb, where b belongs to script b, and that you know. So you can write that you can replace this b prime by fb. Therefore union of fb where b belongs to script b. Here there is a change, you can note that change. Here b prime is in the first part, b prime is used, prime is used or dash is used. Here you can see that that is removed. It's because b prime actually member of the second a typical member of the second space. It can be written equal to fb for some b belonging to the first collection. That's the countable basis. The first collection is a countable basis for x. So where b is an element of script b, and that then can be written equal to f of this union can be taken inside the f of union of b where b belongs to script b. But it is very clear that union of b where b belongs to script b is equal to x. Why? It's because script b make a countable basis for the first space. Thus you can replace this part by x, because this union is equal to capital X. This is used, it's written using the definition of the basis of a topological space, because x because this script b is a basis for the first topological space. It is true. Thus we get that it's equal to this quantity equal to f of x, but f of x, you know, it's equal to y, and thus we get that union of b prime where b prime is an element of script b prime equal to y. This first part contains only this much. Okay, next part, that's the second thing that we need to prove in order to complete the proof that p prime script b prime is a basis for the topological space y. Here we need to choose two members of the collection, the second collection. We choose two members of the second collection. The two members are fb1. You can name them fb1 and fb2. So fb1 and fb2 are two members of the second collection, such that some member is present common to both of these members of the collection. So that means there is the intersection. So we choose two members of the second collection such that x is an element of the intersection of the two members. So x is an element of fb1 intersection fb2. If x is an element of that intersection, and we want to find an open set, in the next step actually we want to find an open set which contains x and is contained in this intersection, in the intersection of fb1 and fb2. So for that we proceed. So let x be an element of fb1 intersection fb2, and then it is clear that b1 and b2 belongs to script b. It is clear. Then b1, then there is b1 and b2 belonging to script b, and also f inverse of x, since x is an element of fb1 and fb2, it is also clear that f inverse of x is an element of b1 and b2 simultaneously. F inverse of x is an element of b1 and b2, so it's an element of the intersection of b1 and b2. Thus there exists a member bx of b. Why? It's because script b is a local it's a basis for the topological space x. Thus, using the definition of the local, using the definition of basis for, it's not local basis, using the definition of actual basis for a topological space, and there must exist a member in that basis. That member is chosen equal to bx. There must exist bx, a member of the basis, such that f inverse of x, it's because f inverse of x is a member of that intersection. So this condition must be then satisfied. F inverse of x is an element of that bx. Bx is a subset of b1 intersection b2. Now we can write that x is an element of, now applying f on both sides here, thus it is clear that x is an element of f of bx. You choose f of bx, the image of the set, the open set bx. So f of x is an element of f of bx is a subset of it's a subset of fb1 intersection fb2, and also f of bx is an element of b script b prime. And that is the element, that is the open set actually we wanted to show that there exists. So f of b1, f of bx, thus f of bx is a member of script b prime with the property that x is an element of f of bx is a subset of f of b1 intersection f of b2. And this was the statement actually we were trying to develop. Okay. So after obtaining this, it is now clear that b script b prime is a basis for y, hence y is also second countable. Thus, assuming that x is x is second countable, and y is a topologically equivalent space to x, we have obtained that y is also second countable, and therefore second countability is also a topological property. Okay, thank you for listening.